Good morning, guys. We're going to review a couple topics that you saw in a video on Thursday. We're going to go a little bit deeper into some of those, and this is effectively the last thing we'll do for the semester. So let's talk about it. We, on Thursday, learned about a concept called standard deviation. If you take statistics next year, if you're interested, you can figure out how to calculate standard deviation, but for our purposes, the most important piece is that it's a measure of, on average, how far is our data from the mean. A higher standard deviation means the data is more spread out. A lower standard deviation means the data is less spread out. The higher your sigma, the more spread your data is. The lower your sigma, the more concentrated or less spread your data that is. And that makes sense. How far is our data from the mean? Well, if we have a really big number, that means our data is really far from the mean. If we have a small number, our data is close to the mean. Let's look at how that might show up for us. Okay, so the first question asks us, which data set has a higher standard deviation, A or B? So when we look at A, we say, okay, the approximate mean is 16, right? It might not be exactly, it's a little weighted toward the 18, but approximately our mean is going to be about 16. And then you look at your data points and you say, well, how far are data points from the mean? Well, all of these data points are 0 units away from the mean. Our 17 data points, those are 1 unit away. Our 15s are 1 unit away. And then our 14s and our 18s are each 2 units away from the mean. When we come over to look at B, similar setup, right? Our mean is still here in the middle, right? But when we look at our data, we say, okay, well, all of these data points are 2 units away from the mean, right? If our mean is 50, all of these data points are 2 units away. And when we look at 48, all of these data points are 2 units away. And so when you're comparing the standard deviation of these two sets of data, for B, our standard deviation would actually be 2, right? Because all of your data, how far is the data from the mean? Well, all of our data is 2 units away from the mean. So on average, a data point is 2 units from the mean. When we look at A, we do have some units that are, or some data points that are 2 units from the mean, but we also have a bunch of data points that are 0 units away from the mean, that are exactly on the mean. Then we have some that are 1 unit away from the mean. So although we have some that are 2, all of these data points that are closer to the mean tell us that our standard deviation, we're not sure what it's going to be, but it's going to be less than 2. So when we look for which data set has a higher standard deviation, it would be data set B. Okay. This data is more spread than data set A. And that's just a visual look. That's just a visual look at it. Let's look at another way you might be asked to talk about standard deviation. So this asks us, which data set is more spread out? Data set A that has a mean of 9 and a standard deviation of 2, or data set B who has a mean of 9 and a standard deviation of 1. Well, if it's more spread out, that means the standard deviation is higher. Well, which standard deviation is higher? Data set A's standard deviation of 2 is higher than data set B's standard deviation of 1. And so which data set is more spread out? That would be data set A. Yes, 2 is greater than 1. Well, let's look at how that might look as a graph, right? Using what we learned on Thursday, where we talked about standard deviation and normal distributions. Let's see what a graph might look like with this information. So we'll graph data set A first. Your mean is 9. So we have a mean here of 9 with a standard deviation of 2. So on Thursday, we learned that you make a mark every standard deviation away. So 1 standard deviation above 9 would be 11. 2 units above that would be, that's actually 13. 2 units above that would be, that's 17, right? So there's 1 standard deviation away, 2 standard deviations away, 3 standard deviations above the mean. And then you go the other way, make the same marks, right? Every 2. So 7, 5, and 3. And then we want to draw a normal curve that follows the empirical rule. So your mean here at 9, And then we follow that normal distribution curve that we saw in the video on Thursday. We just graph a curve, and it might look something like this. Remembering the empirical rule, right? 68% would fall in this range, 95% would fall in this range, 2 standard deviations away, and then 99.7% would fall 3 standard deviations away. Now let's compare that to data set B, who also has a mean of 9. But now the standard deviation is 1, and so we'd make marks 1 unit away, right? So 10, 11, 12. So now that's 1 standard deviation, 2 standard deviations, 3 standard deviations, and we make our marks the other way, right, at 8, 7, and 6. And so 68% of the data now has to fall closer to the mean, and so that would make our curve end up being a little higher. If you're fitting the same amount of data in a smaller space, your curve's going to end up a little higher because our data is now more concentrated with what we learned about the empirical rule on Thursday. 68% of our data has to fall in this area, so it's now more compact or closer together, and so our curve is going to end up looking less spread out. Right, so when your standard deviation is lower, this is less spread. And this would be more spread. The higher your standard deviation, the more spread out your data set. This second page has got some information that we need to know about normal distributions. I'll let you read through that on your own. It's just some useful facts about normal distribution that leads us to a lot of this. In our situation, we're going to pay more attention to the working details, but this is the reason why, right? Our normal curve is bell-shaped and symmetric around the mean. The total area under the curve is 1, so that just tells us that 100% of the data will fall under the curve. And then this is our empirical rule that we learned in the video on Thursday, right? 68% of our data falls within 1 standard deviation of the mean. And because we know the curve is symmetric, if 68% falls within 1 standard deviation, each of these spaces will carry half of that, right? So 34% in this space from the mean to positive 1 standard deviation, and then 34% of the data in this space from the mean to a negative 1 standard deviation. And then we know that within 2 standard deviations of the mean falls 95% of our data. Right? Continuing with our understanding of the curve being symmetric, right? If 68% is here, you've got to go from 68 to 95. Well, half of that extra percentage will fall here for 13.5%. Half of that will fall here for 13.5%, and so on. And then finally, we know within 3 standard deviations of our mean, the empirical rule tells us that that's 99.7%. So to make the jump from 95 to 99.7, that's an extra 4.7%. And so half of that difference will fall here in this section of our curve here, and then half of that difference will fall here on this section. And so we know that the percentage of data in this small little sliver is 2.35%, and the percentage of data in this small little sliver is 2.35%. If you added up every percentage from 3 standard deviations below to 3 above, and you added 2.35 plus 13.5 all the way across, you would get 99.7. And that's how our normal curve works. That's how our empirical rule works. Now let's look at a couple of examples. And so our first example here talks about a box of cereal. On a box of cereal, the weight is listed as 12 ounces. Among all boxes of cereal, the actual weights approximate a normal distribution with a mean of 12 ounces and a standard deviation of 0.1. That makes sense, right? A machine's pumping cereal into those boxes, but it's not going to be absolutely perfect every single time. The manufacturer knows that. And so they give themselves a standard deviation of 0.1, understanding, okay, some boxes might be a little more than 12. Some boxes, unfortunately, might be a little less than 12. But we know that the mean is 12 and the standard deviation is 0.1 ounce. And so we're going to label our curve. We're going to say, okay, well, we know that our mean is 12. And with a standard deviation of 0.1, well, if you go up one standard deviation, that would be 12.1 ounces, and up another would be 12.2. And all we're doing is adding 0.1 each time. So 3 standard deviations above the mean would be 12.3 ounces, and then you go the same gap each unit below. And so 12 minus 0.1 would be 11.9. 11.9 minus 0.1, 11.8, and then 11.7, right? And so all we did was subtract 0.1 ounces all the way down. And that's our curve, right? We know that 68% of the boxes will fall in within 1 standard deviation either way. And that's actually the next question, right? What is the probability that the contents of a randomly selected box of cereal is within 0.1 ounce of 12? So when it says within, that means each way. And so it's asking us, what is the probability that a box is within or between 11.9 and 12.1 ounces. Right? What is the probability that a box is between 11.9 and 12.1 ounces? Well, you come to the curve, you say, okay, here's my 11.9, here's my 12.1. So I'm looking for this area. Well, the empirical rule tells us that if we're looking for those 2 boxes based on the curve on our last page, well, that's a 68% chance, right? 68% of the boxes fall in this gap. And so if we choose one box, the chances that one box falls in this gap is 68%. And then it takes it one step further and says, okay, well, out of 5,000, how many boxes will be within this range? Well, if we know that 68% of all boxes are within this range, then we can expect that 68% of those 5,000 are within this range. And we know to find 68% of 5,000, we just do 5,000 times 0.68. And that gives us 3,400 boxes. Some will be a little bit greater than 12.1 ounces. Some will be a little bit less than 11.9 ounces, but 3,400 of them should be between 11.9 and 12.1. All right, let's look at our second example. So for our second example, scores for a certain professional exam are approximately normally distributed with a mean of 650 and a standard deviation of 100. So it's normally distributed, so we use our normal curve and our empirical rule, and we're going to label our curve. Our mean is 650. Standard deviation of 100. So each standard deviation mark, you go 100 away. So 750, 850, 950. You go 100 away the other way. 550, 450, and 350. And then from here, we're just going to use what we know about the empirical rule and our percentages and what percentage of material is in, or what percentage of the data is in each of these sections to answer our questions. What is the probability that a randomly selected test score is between 350 and 950? Well, let's find our marks. 350 and 950. Well, that's 3 standard deviations above, 3 below. Well, what do we know? Within 3 standard deviations, the empirical rule tells us that 99.7% of all data falls within 3 standard deviations. And using your percentages from our chart, If you added up 2.35 and 13.5 and 34 and 34 and 13.5 and 2.35, that would get you to that 99.9.7% of your data. Let's look at our next question. What is the probability that a randomly selected test score is below 550? Well, you go to 550, and now we care about all of the data below that 550. That would be 13.5%, a 2.35%, and a 0.15%. And so you add all of those percentages up, right? Your 13.5 plus your 2.35 plus your 0.15, and that tells us that 16% of test scores, 16% of test scores will show below 550. Let's look at B. How many randomly selected test scores, how many would you expect to be between 450 and 850? Out of 1,000 randomly selected test scores, how many would fall between 450 and 850? So here we go. We're just going to go to our chart. So, okay, between 450 and 850, and we know that's 2 standard deviations above and 2 below. So if you added up all of our percentages, you know, within 2 standard deviations, that should give us 95%. If you added up your 13.5 and your 34 and your 34 and your 13.5, that gives you 95. But we also know that that's within 2, so that's one of our empirical rule marks. Okay, so 95%. Well, what's 95% of 1,000? 1,000 times 0.95. 1,000 times 0.95, we know is going to give us 950 test scores.